Hello everyone, my name is Bukya Krishna, roll number 20951A2130, branch Aeronautical Engineering, subject Computational Aerodynamics. So today I am going to discuss about compressible flow and rapid prototyping. Coming to compressible flow, dp by d rho by dt is not equal to 0 means the density of a gas changes significantly along a streamline. Definitions of compressibility: the fractional change in volume of the fluid element per unit change in pressure. Here we can see the change in pressure, that is P in the first figure goes to P plus dP, which was the fractional change we can see here. Coming to compressible flow, first Mach number. Mach number is equal to local velocity by speed of sound, that is V by C. And compressibility becomes important for high speed flows where Mach number is greater than 0.3. Mach number is less than 0.3, that we can say as subsonic and incompressible flow. Between the Mach number between 0.3 to 0.8 we can tell as subsonic and compressible flow, and the Mach number between 0.8 to 1.2 we can say it as transonic flow, where shock waves appear mixed subsonic and sonic flow regime, and the Mach number between 1.2 to 3.0 that we can say as supersonic, where shock waves are present but no subsonic flow, and Mach number is greater than 3.0 that we can say as hypersonic flow, then their shock waves and other flow changes are very strong. The significant changes in velocity and pressure result in density variations throughout a flow field, and the large temperature variations result in density variations. As a result, we now have two new variables we must solve for T and rho. We need two new equations. We will solve mass, linear momentum, energy, and an equation of state. Coming to important effects of compressibility on flow, the first one here we want to discuss is choked flow. A flow rate in a duct is limited by the sonic condition, and then sound wave and pressure waves rise and fall of pressure during the passage of an acoustic wave. The magnitude of a pressure change is very small. Coming to shock waves, nearly discontinuous property changes in supersonic flow, that is explosions, high speed of flight, gunfiring, nuclear explosion. Then a pressure ratio of 2 is to 1 will cause sonic flow. Applications: nozzles and diffusers and converging and diverging nozzles, then turbines, fans and applications, and pumps, throttles, new flow regulators, and obstruction in a duct that controls pressure drop, one dimensional isentropic flow, compressible pipe flow. And coming to rapid prototyping, the introduction. In many fields, there is a great uncertainty as to whether a new design will actually do what is desired. New designs often have unexpected problems. A prototype is often used as a part of the product design process to allow engineers and designers the ability to explore design alternatives, test theories, and confirm performance prior to starting production of a new product. Engineers use their experience to tailor the prototype according to the specific unknowns still present in the intended design. Rapid prototyping technology employs various engineering example computer control and software techniques including laser, optical scanning, photosensitive polymers, material extrusion and deposition, powder metrology, etc. to directly produce a physical model layer by layer, that is layer manufacturing, in accordance with the geometrical data delivered from a 3D CAD model. Here we can see the differences between conventional machining and rapid prototyping. Coming to conventional machining, produce a model by removing material bit by bit. And coming to rapid prototyping, produce a model by adding material layer by layer. Coming to conventional machining, it is subtraction process, and rapid prototyping is a addition process. Coming to conventional machining, it is limited, And coming to rapid prototyping, it is unlimited. Why rapid prototyping? Prototyping can improve the quality of requirements and specifications provided to developers and reduce time and cost. Users are actively involved in the development. Quicker user feedback is available, leading to better solutions. Errors can be detected much earlier. Missing functionality can be identified easily. Coming to limitations of rapid prototyping, high precision RP machines are still expensive. RP systems are difficult to build parts with accuracy under plus or by plus or minus 0.02 mm and wall thickness under 0.5 mm. The physical properties of the RP parts are normally inferior to those samples that made in proper materials and by the traditional tooling. The RP parts are not comparable to CNC prototype parts of in the surface finishing, strength, elasticity, reflective index, and other material physical properties. Coming to workflow of RP processes, all rapid prototyping techniques employ the basic 5 steps processes. Coming to first one, create a CAD model of the design, and the second one, convert the CAD model to STL form. And coming to third, slice the STL file into the thin cross-sectional layers. And the fourth one, construct the model one layer atop another. And the fifth one is clean and finish the model. This is the workflow of RP process: a CAD model, pre-processor, RP process, and post process. In CAD model, the surface and solid model is presented. Then it can convert it into generate STL file, build supports if needed, and slicing. Then build prototype and remove supports, clean the surface, post cure, part completed. There are several types of rapid prototyping technologies. They are SLA, SLS, LOM, FDM, and 3DP. Coming to SLA, it is stereolithography and selective laser sintering, laminated object manufacturing, fused deposition modeling, three-dimensional printing. Thank you.